In this video, I'll talk about software build process and the tools used for this process. In software, build usually means the process of taking a project, including its source code, metadata files, resources, and libraries, and package them in a format or formats for execution, distribution, and/or deployment. For many people, when they see the build button in an IDE, they just think of it as compiling the source code. But for a non-trivial project, build often involves a lot more than just compilation. For example, before compilation, you may have a pre-processing step that generates code from annotations and other metadata. And after compilation, you may have a post-processing step linking different object files together. Things like testing, packaging, even distribution and deployment can all be part of a build process. Now let's look at an example. This example uses the programming language C. If you don't know C, it's perfectly fine. The code is very simple to understand, plus we just want to look at the build process. The code itself is not important. So here I have a function that calculates the average of two numbers. And here I have a header file, which contains the header of the function. In C, a header file is like an interface in Java. It defines the API without implementation. And then here, I have a main function which uses the average functions to calculate the average of a couple of numbers. Again, the details of the code is not important. Despite the code being quite simple, the build process is not. Here are what we need to do. First, we need to compile the main file to produce an object file. An object file cannot be executed directly, but it can be linked with other object files to produce an executable file. We then want to create two types of libraries from the main function. The reason we want to create two types of libraries is because they each have some pros and cons. Specifically, when we link to a dynamic library, the functions in the library are not included in the executable file, so the size of the executable file can be small, but when you run it, you have to have the dynamic library around. If we link to a static library, the functions used in the main program are included in the executable file. So the size of the executable file is larger, but you don't need the library anymore when you run it. In any case, if you're not too clear about the differences between dynamic and static libraries, it's fine. Again, our focus is on the build process, and the main purpose of this example is to show that even when the code is simple, the build requirements can be complex. So obviously, we don't want to do all this manually every time we change some code. And this is where build tool comes in. The build tool we'll use is called make, and this file is called a make file, which contains the rules to build the project. This is what a makefile rule looks like. The purple part is called target, which is the name of a file or some operation. The blue part is the prerequisites, which are the files or other targets that are needed to build this target. The rest of it is called recipe, which are the actions to achieve the target. Again, the details here are not important. If you don't know what, for example, -d is or what AR is, that's perfectly fine. Just know that there are some actions to produce the file libmin.a. Excuse me. So to use make, just type either make, which will try to build the first target of the make file, or type make, then target name. So just like this. These are the files, and if we type make, it will try to build the first target of the make file, which is usually called all, which usually builds everything. So if we do make, we can see that it now creates a bunch of new files, 2 executable files, and the lib folder, and inside the lib folder, 2 libraries, 1 static library and 1 dynamic library. And we can also specify a target to build. For example, if we want to remove all the generated files, we have a target here called clean, and if we do make clean, it will remove all the generated files and folders, and now we are left with just the source code again. So make is an example of a build tool, and the make file is often called a build file or build script. A build script typically consists of a number of small programs called recipes in make that implements various build tasks. The build tool is responsible for executing a build script intelligently and efficiently. For example, it won't recompile a source file if it's not changed, and it will automatically build a prerequisite if a prerequisite is not met. At this point, you may be wondering, why don't we just use an IDE like Eclipse or Visual Studio? The answer is that if an IDE meets all your needs, then great, you really don't need any other build tool. However, that's often not the case. For example, what if you want to deploy a web application to a remote server, or generate source code from some metadata files, or create a zip file of selected files of a project for homework submission? There are many tasks like this that may not be supported directly by your IDE, and this is where you'll need a build tool. A build tool essentially provides a mini programming language that can be used to implement any build task. In fact, many IDEs have integrated build tools, like Visual Studio with MS Build, Eclipse with Maven, and Android Studio with Gradle. The IDE provides a GUI to the build tool, and the build tool does the real work. Now coming back to Make. Make was a popular build tool for C and C++ programming language, but it has a big problem. It uses system commands and shell scripts as its programming language to implement the build tasks, and that makes it platform dependent. For example, the command to copy a file on Windows is copy, C-O-P-Y, but on Linux it's just CP. So if you have a make file that works on Windows, it won't work on Linux because the commands it's used for the recipes are all different. When Java first came out, people needed a new build tool for Java because Java was platform independent. Also, the Java compiler works a little different from a C compiler, so using Make for Java not only would be not platform independent, but also would be not efficient. So an engineer from Sun Microsystems, James Duncan Davison, who by the way also wrote the Tomcat server, developed a new build tool called Ant. Many years ago, when we developed the first version of CSNS, we actually used this Ant build file to build the project. I highlighted some parts of the build file here, and you can see the similarity between Ant and Make, like target, like the commands, and like the prerequisites, which are now called dependencies. This table summarizes these similarities. As we can see, Ant was clearly modeled after Make, with targets and dependencies and so on. The biggest difference is that Make relies on system commands and shell scripts, while Ant replaces them with XML tags, which are system independent. Another important thing to notice here is that shell script is a real programming language that you can use to implement pretty much anything, while these XML tags like sequential, conditional, retry, and so on only provide limited programming capabilities. Neither Ant or Make is used much these days because they miss two important things in modern build tools. First, they don't have dependency management or package management. Dependencies here mean the libraries that a project uses, not the target dependency in Ant or Make. A project these days often uses lots of libraries, and it's important that your build tool helps you to manage these libraries. Another problem with Ant and Make is that they don't promote or enforce a standard build process, so each build is different. Even if you are a build expert, it will take you a very long time to learn the build process of a complex project. So this takes us to the first build tool you need to learn for this class, Maven. Maven has been the main Java build tool for many years. It has several components. Project Object Model, or POM, is used to describe a project. Project lifecycles define the standard build processes. Dependency management manages the libraries used in a project, and the plugin framework allows new functions to be added to Maven. Let's start with a simple example. I have a Java program here. The code is very simple, just printing out hello. And this pom.xml file is a build file used by Maven, like make file used by Make. And POM, of course, stands for Project Object Model. It's Maven's way of describing a project. We see that the POM file is pretty simple too, just a few XML tags. We'll explain what they mean in a moment. Now, let's say I want to compile the code. So, here's the project folder. And notice that right now I only have two files in here, hello.java and pom.xml. If I want to compile the code, I'll type mvn compile. And if we check this folder again, we can see that it compiles the Java code and produced a class file placed under a new folder called target. And if I want to package the code, I'll type mvn package. And if we check again, we can see that now it creates a jar file under the target folder. So how does it work? In Maven, the POM file is a complete description of the project. We can see that it's an XML file with some tags. These tags, like project, model version, group ID, and so on, constitutes a markup language that can be used to describe a project. Project Object Model is the name of the language, and the model version specifies the version of the language used to describe this particular project. This is not too different from HTML. You have, for example, HTML version 4, HTML version 5. Each defines a set of tags describing a web page. The difference here is that the tags here are used to describe a project instead of a web page. So what about group ID, artifact ID, and version? These three elements, together with packaging and classifier are known as Maven coordinates. Maven coordinates are used to uniquely identify a project, just like coordinates are used to locate a point in space. In particular, group ID is the name of the company, organization, team, etc., usually using the reverse URL naming convention. Artifact ID is the name of the project. Version is, of course, version. Packaging is how the project will be packaged, and is also used to indicate the type of the project. For example, a desktop Java application will use jar packaging, while a Java web application will use var packaging, WAR. If packaging is not specified, it defaults to jar. Classifier is an optional coordinate that specifies additional information of the project. For example, if it's for 64-bit Intel architecture, it could be x64, or if the project is intended for an older version of JDK, it could be something like JDK 1.2. So, for example, if I create a project for homework 1 in this class, the Maven coordinates could be something like this. So the first part of the Maven coordinate is group ID, typically using the reverse URL naming convention. So, for example, my group ID could be edu.csula.cs5220.cysr. And then the second part is the artifact ID, which is a project name. In this case, if I'm doing a whole project for homework 1, it could be homework 1. And then the third part is, of course, version number. And I'm omitting packaging and classifier because packaging has a default and classifier is optional. So here you can see that project names are often not unique. I can have a homework 1 project and you can have a homework 1 project. But if we combine all the Maven coordinates together, it makes sure that we can uniquely identify a project. So what if we don't have all the coordinate stuff and just use project name as the identifier? Well, that's actually how Node.js packages work. It works for the most part, but occasionally it runs into problems when people have a dispute on a particular name. You can check out this linked article for one of those stories. So now we know what these tags are. We realize that this pom file really doesn't say anything about how the project should be built. Well, this is because as most software systems these days, Maven takes a convention over configuration approach, meaning that it has lots of defaults that you don't need to explicitly specify. If you want to see what all those defaults are, you can open up a pom file in Eclipse, then select the effective pom tab, like this one. So here is a pom file inside Eclipse. It's the same as the one that we just saw. Very simple, just some coordinates tags, model version, nothing else. However, if you click on the effective pom tag, you can see that this simple pom file is equivalent to a much complex one with all the defaults spelled out. You don't really need to know most of those defaults, except for one thing, the default directory structure. In a Maven project, there are usually 2 folders. source and target. Source is of course for source files, and target is for generated files like class files. Inside source, there are main and test, one for application code and one for test-related code. And then inside main, Java source code is under Java, files that should be placed under class paths, usually configuration files, are under resources, and web application files like HTML, CSS, JavaScript files, and so on are under web app. You could configure Maven to use a different directory structure, but there's really no good reason for that. Just understand and follow the default directory structure. It also makes it easier for you to understand other people's projects. So now that we know how a Maven project is structured, the next question is how do we build it? In other words, what happens when we run mv and compile, for example? The answer is that Maven will go through each phase of the build lifecycle up to the compile phase and run the operations associated with each phase. There are obviously several things here that need to be further explained. For example, what is a build lifecycle? What's a phase and what are the operations? Build lifecycle is a process for building and distributing a project. And the build lifecycle consists of a number of steps called phases. What's kind of unique about Maven is that it defines a few standard build lifecycles, basically saying that regardless of what project you have, your project can use these build lifecycles. So if we go to this web page, which I already opened here, we can see that there are three standard build lifecycles Maven defines: clean, default, and site lifecycle. The clean lifecycle is for cleaning a project, and the site lifecycle is for generating documentation. These two are not important. The important one is the default lifecycle, which, according to Maven, has all the steps needed to build any project. We can see that this default lifecycle starts with a validate phase, then initialize, then generate sources, then process sources, and so on and so forth, all the way to verify, install, and deploy. That's certainly lots of steps or phases in the standard build lifecycle. What if our project is not this complex? Well, that's perfectly fine. The standard build lifecycle specifies all the possible phases, but not all projects need to use all of them. For a project, most phases can be empty, meaning that there are no operations associated with the phase. For example, when we type mv and compile, we're telling Maven to go through each build cycle's phase up to the compile phase and perform the operations associated with each phase. Note that by default, there are actually no operation associated with phases like validate, initialize, and so on. The first operation we'll actually encounter is in the process resources phase, and this operation simply copies the resource files to the class path. And in the next phase, the compile operation compiles the source code. So this is basically how Maven build works. It simply goes through each phase up to the one you specify and run the operations associated with each phase. And these operations are provided by Maven plugins, and their official names are called goals. You can see the built-in Maven plugins here. And if you click on a plugin, you can see the operations they provide. For example, we can have a look at the compiler plugin. Notice here that this compiler plugin provides two goals, a compile goal and a test compile goal. The compile goal is associated with the compile phase, or in Maven terminology, bound to the compile phase, and the test compile goal is bound to the test compile phase. Usually a goal has some configuration parameters that you can use to customize it. For example, you can customize the compile goal by adding this to a POM file. Here it basically says that the compile goal will produce JDK 1.7 compliant class files. Another thing to note here is that a Maven plugin itself is also a software project, so it has its own Maven coordinates, group ID, artifact ID, version. To summarize, to build a Maven project, you specify the phase, and Maven will go through each build's lifecycle phase up to the specified one, and in each phase, execute the goals bound to that phase. And we can do this in Eclipse too. So in Eclipse, right-click on a Maven project and select Run As, and you can select Maven builds. There are a few predefined Maven builds like build, clean, generate, sources, install, and so on. You can create your own by specifying a name, and then in the goals field, just type in the phase, the name of the phase, and then click run. It will do what we did here. Same as just type mv and compile, and here you can do the same thing in Eclipse. If we compare Maven and Ant and Make, we can see that there's no user-defined target in Maven. Instead, Maven has some predefined phases. Maven also doesn't have arbitrary prerequisites. Any previous phases that are before the current phase are actually considered the prerequisite of the current phase. And for actions, Maven have goals. However, you can only customize goals, but you cannot use them to program anything new. If you really need to do something that's not provided by any existing plugin, you'll have to write your own plugin. So, no program capabilities, except that you can create new plugins. What this comparison tells us is basically that there's a trade-off between standardization and flexibility. You can have a flexible build tool like Ant or Make that lets you do anything you want. But the downside is that every build process is different, so learning a build process itself can be difficult. On the other hand, you can use Maven, which standardizes the whole build process, but it may be difficult if you want to do something outside the box. With that said, Maven definitely has one huge advantage over Ant and Make, and that's dependency management. Again, here a dependency of a project is a library that the project depends on. In Maven, adding a dependency to a project is as simple as adding the coordinates of the library to pom.xml. Maven automatically downloads the library from an online repository and stores it locally for future use. For example, if we want to add a servlet-API dependency to our project, we just need to copy this to a POM file. It's even easier in Eclipse as we can search for the dependency. So here, for example, open up the POM file and go to Dependencies tab, and then click Add, and then you can search for it. So let's say we want to add something called servlet-API, and there are a whole bunch of them. They do have different group IDs and stuff. And the one we want would be this one with group ID javax.servlet, and we can pick the version we want. And if we look at the POM file, it's basically adding this section to the POM file. And if we click Save, Maven will automatically download the jar file, include the library into the project. Maven not only gets the dependency itself, but also the dependencies of the dependency, and it also automatically resolves dependency conflicts. Take the dependencies in CSNS as an example. So this is the CSNS source code, and this is the Maven POM file of CSNS. If we look at dependencies, you can see that CSNS uses a bunch of libraries, and if you look at dependency hierarchy, you can see that it includes even more dependencies, because some dependencies has their own, and sometimes you have dependency conflicts which are automatically resolved by Maven. So in the end, these are all the dependencies included in the project. So this is enough about Maven for now. And now we need to talk about the second build tool that you'll use a lot in this class, npm, the Node Package Manager. npm is a dependency manager for Node.js with some build support. For those of you who are not familiar with Node.js, it's basically JavaScript, but you can run it outside the browser. It's very, very popular in web development because A, its asynchronous and event-driven design makes it very efficient to process high volumes of web requests, and B, it allows you to use the same language for both back-end and front-end development. The build file used by npm is package.json. When you create a new Node.js project, you can do a npm init to create a package.json file. For example, here, let's create a new folder called npm example, and go inside the folder and type npm init. It will ask you a bunch of questions, package name, version, so on and so forth. So we leave everything to default, and we can see that here is a package.json file, which is basically this. To add a dependency to a project, just do npm install and then the package name. For example, we can add a request dependency to the project. Request is a very popular Node.js package that you can use to send requests to web applications. So we can do npm install request. I think I mistyped request. Oh, there's actually something called request. That's interesting. Well, fortunately, we don't really need to use it for real. But by the way, this is another reason using package name is probably not the best idea, because you can have a typo and including a library that is not what you really want. And if this is something malicious, for example, if I'm a hacker and I can create a package that looks very much like another package but does some malicious things, it's a potential security risk. So going back to Maven coordinates, it's probably better to have things like group ID to help distinguish different libraries and dependencies. But I digress. Coming back to this, so notice that if you look at this, it's not too different from POM, right? In POM or in Maven, if you want to include a dependency, you include the version, the Maven coordinates, and then Maven automatically grab the library for you. And same thing here. There is, however, a big difference. Instead of just a version number, it gives you something extra, like a cap here. So what does that thing mean? To understand that, first we need to understand the so-called semantic versioning. NPM packages uses the so-called semantic versioning, meaning that each version number consists of 3 numbers: the major release number, the minor release number, and the patch release number. The convention is that if the updates to a project breaks backward compatibility, you have to give it a new major release number. If the updates add new features but don't break old ones, you only increase a minor release number. And if the updates are only bug fixes and minor changes, you only increase the patch release number. This way, people can have some idea about what a new version does just by looking at the version number. In package.json, oftentimes you'll see either a cap or tilde in front of a version number. A cap means that this dependency can be automatically updated to any future minor releases, while a tilde means it can be updated automatically to any future patch releases. NPM, as the name suggests, is primarily a dependency manager, but it does have some build support, which in the scripts section of the package.json. NPM has a number of commands corresponding to common build tasks like test, start, stop, pack, and publish. And similar to Maven build cycle phases, each NPM command may have stages. For example, the test command has pretest stage, test stage, and posttest stage, in which actions can be performed. Like make, NPM relies on system commands and external tools for basic actions. For complex build tasks, the choices are either programming them in JavaScript or use additional build tools like Grunt or Gulp. We'll talk more about NPM when we get to Node.js development. And here are some additional readings if you want to know more about the build tools we covered today. See you in the next video.